A quick new idea daily from the world's greatest TEDx talks. I'm your host, Atosa Leone, and this is TEDx Shorts. Science has made a lot of progress mitigating the effects of heart disease, but it's still one of the leading causes of death worldwide. Physician and scientist Chuck Murray has a plan: restoring contractile heart function with stem cells. The trick is getting these cells to interact appropriately with the muscle. But as he explains today, we may not be far away from that reality.
The heart is the least regenerative organ in the human body. We've resigned ourselves to this as the status quo because we have to. Or do we? I think there's a better way, and this better way involves the use of stem cells as medicines. They're just simple little round cells, but that belies two remarkable attributes. The first is they can divide like crazy. So I can take a single cell, and in a month's time, I can grow this up to billions of cells. The second is they can differentiate or become more specialized. So these simple little round cells can turn into skin, can turn into brain, can turn into kidney, and so forth. The heart lacks stem cells entirely. So for the heart, we're going to have to bring stem cells in from the outside. And for this, we turn to the most potent stem cell type, the pluripotent stem cell. Pluripotent stem cells are so named because they can turn into any of the 240-some cell types that make up the human body. So this is my big idea. I want to take human pluripotent stem cells, grow them up in large numbers, differentiate them into cardiac muscle cells, and then take them out of the dish and transplant them into the hearts of patients who've had heart attacks. I think this is going to reseed the wall with new muscle tissue, and this will restore contractile function to the heart. Our first experiments worked, sort of. We got these little clumps of beating human heart muscle in the dish. And that was cool because it said, in principle, this should be able to be done. But when we got around to doing the cell counts, we found that only 1 out of 1,000 of our stem cells were actually turning into heart muscle. So how do you coax a cell that can become anything into becoming just a heart muscle cell? Well, for this, we turn to the world of embryology. And for over a century, the embryologists have been pondering the mysteries of heart development. And they had given us what was essentially a Google map for how to go from a single fertilized egg all the way over to a human cardiovascular system. So we shamelessly absconded all of this information and tried to make human cardiovascular development happen in a dish. It took us about 5 years, but nowadays we can get 90% of our stem cells to turn into cardiac muscle, so a 900-fold improvement. We took a gene from jellyfish that live in the Pacific Northwest, and we used a technique called genome editing to splice this gene into the stem cells. And this makes our heart muscle cells flash green every time they beat. Okay, so now we were finally ready to begin animal experiments. We took our cardiac muscle cells and we transplanted them into the hearts of rats that had been given experimental heart attacks. A month later, I peered anxiously down through my microscope to see what we had grown. And I saw nothing. Everything had died. But we persevered on this, and we came up with a biochemical cocktail that we called our pro-survival cocktail. And this was enough to allow our cells to survive through the stressful process of transplantation. And now, when I looked through the microscope, I could see this fresh, young human heart muscle growing back in the injured wall of this rat's heart. So this was getting quite exciting. The next question was, will this new muscle beat in synchrony with the rest of the heart? So to answer that, we returned to the cells that had that jellyfish gene in them. We used these cells essentially like a space probe that we could launch into a foreign environment and then have that flashing report back to us about their biological activity. Of a guinea pig's heart that was injured and then received 3 grafts of our human cardiac muscle, and they're flashing in synchrony back through the walls of the injured heart. What does this mean? It means the cells are alive, they're well, they're beating, and they've managed to connect with one another so that they're beating in synchrony. In other words, the guinea pig's natural pacemaker is calling the shots, and the human heart muscle cells are following in lockstep like good soldiers. So our current studies have moved into what I think is going to be the best possible predictor of a human patient, and that's into macaque monkeys. You'd think that we hit all the roadblocks that lay in our path, right? Turns out not. These macaque studies also taught us that our human heart muscle cells created a period of electrical instability. This was quite unexpected because we hadn't seen this in smaller animals. And it turns out that it results from the fact that our cellular grafts are quite immature. And immature heart muscle cells all act like pacemakers. So what happens is we put them into the heart, and there starts to be a competition with the heart's natural pacemaker over who gets to call the shots. So our plans at the moment are to make the cells go through this troubled adolescence period while they're still in the dish. And then we'll transplant them in the post-adolescent phase, where they should be much more orderly and be ready to listen to their marching orders. So one big question still remains, and that is, of course, the whole purpose that we set out to do this. Can we actually restore function to the injured heart? In every one of the animals that received a graft of human cardiac muscle cells, we see a substantial improvement in cardiac function. This averaged 8 points, so from 40 to 48%. So going forward, our plan is to start phase 1, first-in-human trials here at the University of Washington. Presuming these studies are safe and effective, which I think they're going to be, our plan is to scale this up and ship these cells all around the world for the treatment of patients with heart disease. And when this happens, it's going to have a transformational effect that rivals the development of vaccinations and antibiotics.
Scientific ideas are always subject to change as researchers learn more. For more details and context on this talk, check out the footnotes on TED.com. The TEDx talk you just listened to was recorded in Seattle, Washington. All TEDx events are independently organized by volunteers who believe in TED's mission of ideas worth spreading. Special thanks to the organizing team at TEDx Seattle. Want to listen to more TEDx talks? Explore the entire archive on the TEDx YouTube channel. I'm Atossa Leone. Thanks for listening, and see you tomorrow.